Hi again. I have some questions on the story problems on 715. So I didn't go back and watch the 17 video or 715 video, but you might be wondering, why are we all of a sudden introducing vectors? Isn't this a physics thing? And the answer is yes. However, um, for your whole life up until now, you have done mathematics using the point system, where the graph of any function is defined as where a bunch of points show up. So, for instance, a sine graph looks like this, and it's defined by a whole bunch of points. And we haven't really had any trouble doing mathematics using the point system, using the function system, which is really nice. You pick an x value, you plug it in the function, you get a y value, and you graph it. And you can do all sorts of things with that information. And when you move on to calculus, which I hope you will because it's a fantastic class, you will be doing calculus using the point system, which is not too bad in 2 dimensions. It's not super complicated. Well, I mean, compared to some things. And then in Calc 2, you're going to kind of shift gears and do some other graphing things. But in Calc 3, you move into 3 dimensions. So you have an x and a y and a z. And you can do calculus in 3 dimensions using the point system. It works. It's just really, really complicated. So instead of the point system, we move to the vector system. So instead of describing things as a point, we describe them as a vector. And it turns out that the dot product and something called the cross product and some other matrixy things all come together, and you find out that doing calculus with vectors is so much easier than doing calculus using the point system. In fact, when you get to Calc 3 and you learn that, you realize, man, we should have done that from the beginning in 2 dimensions. It would have been way easier. And that's true, but it would have been harder to understand in the beginning. So vectors play a role. They're not necessarily a trigonometry topic, but you do use the cosines to find the angles and that kind of thing. But let me see if I can help you out a little bit with the story problems on 715. So let's suppose that I had a big heavy weight that had wheels on it. And I'm going to pull on it. Well, let's say that this weight weighs 100 pounds. If I tried to lift straight up in the air, and I'm only strong enough to lift 50 pounds, I could pull all day long. And even though I'm working really, really hard, no actual work is accomplished. Nothing actually moves. Okay? Well, if I'm able to pull straight across, then if I'm strong enough, I can get that weight to roll. It's on wheels, so it probably isn't going to take 100 pounds. It just depends on how much friction there is in the wheel bearings and between the wheels and the ground. But I can pull it. And depending on how far it moves and how much energy it actually takes to move, I can calculate how much work is done. And work is measured using 2 units. It's a distance and a weight. So you could say I moved 70 pounds worth of weight 2 feet. So if it takes 70 pounds to pull this, and I move a distance of 2 feet, then the formula is just the how much effort it took to move it and how far I moved it multiplied together. So that equals 140 foot-pounds. Okay, now that doesn't tell me how hard I pulled. That just tells me how much effort it took to move that. It took 70 pounds. Now, and maybe 70 is really high, I don't know. But if I were to take the wheels off this block, now to drag that instead of 70 pounds, maybe it takes 98 pounds to move that same weight. There's more friction. So if I move if I pull with 98 pounds of force and it moves 2 feet, then the amount of work done would be 196 foot-pounds. Oops, I didn't put pounds up here. Okay. Well, something else happens that's really interesting. What if I put the wheels back on, and this is a little tiny short thing, so here I am standing up, because I'm nice and tall, you guys know that, and I've attached a rope to my arm, and I'm going to be pulling. Well, I'm kind of doing myself a disservice here. We know that if I pull straight across, then that weight is going to roll in that direction. But if I pull straight up and down, it doesn't matter how hard I pull, it will never roll the direction I want it to roll. If I'm strong enough, I could lift it off the ground, but if the goal is to get the weight from here to here, pulling straight up isn't going to accomplish anything. So pulling directly horizontal will move the weight horizontal, and all of the effort I give will go into moving that weight in the direction that I want it to move. But if I pull straight up and down, none of the energy that I use will go towards the task that I want it to accomplish. And it turns out that pulling in all of these other angles will yield some percentage of force that actually moves in the direction that I want. So what I'm saying is, if I pull in this direction, I'm wasting energy, because I'm pulling up and over, and none of the energy that is going in the up direction is actually going to help the weight roll. It's just going to be lifting a weight that doesn't get lifted because it's too heavy. So there's a way to figure out how much work is done if I pull at a strange angle. And pulling at a strange angle will actually make you lose energy. You'll be working harder than you need to move the weight. And you say, okay, why do we care? Well, this sort of thing happens all the time. So let's say that you have a big oil tanker whose engine exploded, and you need to tow it 3 miles to port, right? It almost made its trip, didn't quite get there, engine died. We can't just have it floating around in the ocean. We need to tug it into port. Well, if we have a tugboat, then we would take that tugboat and we would pull in this direction. But let's say that the tanker is so large and it has so much oil in it that one tugboat is not going to be enough to move it. So we need 2. But there's a problem. If I connect 2 tugboats to this, they're going to be banging into each other and breaking. It's just not safe. So instead, what we do is this. Okay, we put one tugboat here and one tugboat here. And now we have a problem, because if this tugboat points straight at the port and this tugboat points straight at the port, you can kind of see what's going to happen. They're going to slowly merge together and eventually they're going to hit. Right? So those tugboats cannot be pulling parallel to the direction they want to travel. Otherwise, the weight of the tanker is going to yank them together and they're going to hit each other, and it's just not safe. So what we do is we attach the 2 tugboats, and instead of aiming them straight at the port, we aim them kind of angled toward the port, like this. And now, because they're not aiming in the same direction, they're not going to slide together and hit each other. Well, the problem is, let's say that this tugboat can pull, I don't know, 3,000 pounds of force, and this tugboat can pull 4,000 pounds of force. Well, together that's a total of 7,000 pounds. So is all of that 7,000 pounds reaching the tanker? And the answer is no. We lose some of it. How much do we lose? Well, we kind of make a right triangle, and this force, this force right here is 3,000 pounds. Okay? And this force here is 4,000 pounds. But because I'm not pulling straight in the direction that I want the tanker to move, I'm going to lose some of that energy. And it turns out that this angle or that side right there might be, I'm just guessing, but it might be 2,500 pounds. And this vector right here might represent 3,200 pounds. Okay, so how much force is actually hitting the tanker? It's going to be this plus this, which is 5,700 pounds. And some of the force is wasted. And this happens all the time. It's very, very common for us to pull in a direction that is not exactly in the direction we want the object to move, but we need a way to calculate how much force is actually happening. Okay, so story problems. Let me grab my book. So let's do this example right here. All right, so that's not very good. So we look at this guy whose car has died, and he wants to move the car, and you can see by the angle of his arms, he's pushing in this direction. Why is he pushing in that direction? I don't know. That's just the way he's pushing. But the car needs to move in this direction. So you can see some of his energy is wasted. So this length is the amount of energy he's expelling, he's actually exerting. And this is how much of that energy is actually going into moving the car, because he's not going to push the car through the cement. Right? He can't sink it into the ground. So only the horizontal piece of this is going to move the car. So if we turn the page, oh, you can't really see that. Sorry. So we often want to know how much of a force is applied in a certain direction. For example, when your car runs out of gas and you try to push it, some of the force vector F1, so F1 is the direction we're pushing, translates into the F2 direction. That's the way that the car is going to move. So we let theta be the angle between vectors F1 and F2. Then the horizontal component of F1 is F2, where F2 is the magnitude of F2 is the magnitude of F1 cosine of theta. Okay, that's really confusing. What it's saying is, if you know how long this vector is, and you know the angle between the two vectors, it's very easy to calculate the length of that vector. How do we do it? Well, we take the magnitude of f. So the magnitude of f is basically the Pythagorean theorem. So it's the square root of x squared plus y squared. Okay, and then we're going to take that and times it by the cosine of theta. Okay, well, if the man pushes at an angle of 25 degrees with a force of 150 pounds, then the horizontal component of the force vector is 150 pounds times the cosine of 25, which is 136 pounds. So this number right here is, so if we had this picture, we would just take, it's the distance formula. So how far is it this way squared, how far is it this way squared, and then take the square root. Okay, but they told us it's 150 pounds, which is kind of nice. So what does that mean? Well, it means that when the man exerts 150 pounds of force in this direction, 136 pounds of that force will hit the car. So it's essentially like pushing the car horizontally at 136 pounds. Now, if you were smart, you would not push at an angle. If you have 150 pounds of force to use, then by all means, don't push in this direction. You're just wasting it. Instead, push in this direction, and then all 150 pounds will hit it. But you get the idea. that when you push at an angle, you lose energy. 150 turns into 136 or whatever it was. 136. Okay. So, look at number 41. So there's a crate on the floor, and you have 50 pounds of pulling power, and you are pulling at a 30-degree angle from horizontal. How much work is done if you drag that crate 30 feet? All right, so from here to here is 30 feet, and you're pulling at 50 pounds at a 30-degree angle. Well, not all of your 50 pounds is helping the crate move. Some of it is simply wasted because you're pulling in the wrong direction. Now, if you were to pull straight up with 50 pounds and the crate weighed, say, 60 pounds, then even though you are working very hard, none of that energy is going to translate into work. You're going to get sweaty and tired, but the crate isn't going to move. Nothing actually happens. It's like going and pushing a mountain. You can push as hard as you want against a mountain, but you're not strong enough to move it, so no work is accomplished. Okay, so we need to figure out how much of this 50 pounds is going to be exerted in moving that crate horizontally. Well, the formula is easy. It's just the magnitude of your force vector times the cosine of the angle that you're pulling at. So 50 pounds is the magnitude of F, that's how long the force vector is, times the cosine of 30 degrees. So 50 times cosine of 30 gives us 43.3, which means 43.3 pounds of our force is actually going to go towards moving the crate. And we move the crate 30 feet, so 43.3 times 30 is 1299. So 1299 what? Foot-pounds. That's how much work I did. I exerted 1,299 foot-pounds. Okay, I exerted 43.3 pounds of work over a 30-foot distance. So this gives me a total in foot-pounds. Okay, now what if I was smart and I pulled things horizontally, which is what you should do if you can, but it's not always possible. So now I'm pulling in this direction with a force of 50 pounds, and I move that a distance of 30 feet. Well, I can just times those together and I get 1,500 foot-pounds. But what if I use the formula right here? 50 times the cosine of, what's my angle? Well, the angle between where I'm moving and where I'm pulling is 0 degrees. And the cosine of 0 is 1. So I get 50 times 1, and then I times it by 30. So if you're pulling in the correct direction, which is a 0 degree offset angle, then all of your force is going to be exerted in moving the box. Okay, I hope that helps you with the next problem, the other story problems. If not, let me know, and I can work those too.